In this video, we're going to be discussing centripetal force, torque, and universal gravitation. Centripetal force is a center-seeking force, which is where centripetal comes from. So any force that causes an object to move in a circular pathway would be called a centripetal force. So the object will experience what is called a centripetal acceleration. So even if the speed is constant, it's always changing direction. So remember that for there to be acceleration, one of three conditions have to be met: speeding up, slowing down, or changing direction. In a lot of cases, the speed will remain the same, but it's the direction that changes. Therefore, we have an acceleration. And it just so happens the acceleration points toward the center. So a few examples of centripetal acceleration are gravity keeping the moon in orbit around the Earth. Gravity keeps the Earth in orbit around the sun. So gravity is providing that centripetal force that keeps the moon in orbit around the Earth and the Earth in orbit around the sun. Another example is the friction between the tires and the road allows the car to go around a curve. So the car will experience a centripetal force as it moves around the curve thanks to the friction. You may hear this something called a centrifugal force or centrifugal force. This is a fictitious force. It's not an actual force. It's actually caused by the object's inertia. So the object keeps wanting to move in a straight line according to Newton's first law of motion. Now, if the centripetal force diminishes or disappears, though, the object will move in that straight line due to inertia. So as a car goes around an icy curve, it will still want to sort of move in the direction it was initially going. In lab, what you might end up using is a rubber stopper around a swing, and if you keep spinning it in a circle and you cut the rope, it would go out in a straight line. It's also, if you go around a curve as well, and you'll notice in your car some of the things will slide out toward the curve, and again, it's because those objects are wanting to continue in a straight line. It's not due to any force at all. It just, the law of inertia allows them to continue moving. So it's not part of an interaction between forces or anything like that. There's no reaction force involved. It's just inertia. All right, so let's look at our equations for centripetal force. You'll have practice with this in class. So centripetal acceleration, we use A for acceleration, and we do a little subscript called C, so we know that this is centripetal acceleration. And A sub C equals V squared, which is your velocity squared, divided by the radius of the circle that involves the circular motion. Your centripetal acceleration will, of course, in this case, be measured in radians per second squared or meters per second squared. Your velocity, of course, meters per second, and your radius will be measured mostly in meters. Now, your centripetal force again measured in newtons. We do an F sub C, so we know it's centripetal force, and so we'll multiply the V squared over R by the mass, giving us m times v squared divided by r, which gives us our more familiar form of Newton's second law, which is F sub c equals mass times centripetal acceleration. So just so you know that even with centripetal forces, Newton's second law of motion will still apply. You have an unbalanced force applied to a situation which points toward the center, which causes an acceleration to occur. And that acceleration just also points toward the center as well. So let's go ahead and talk about torque. Now, torque is used to change rotational motion. Torque actually causes that centripetal acceleration that you see. So it can be used to start, stop, or change any type of circular motion. And it is the product of the force times the length of the lever arm. And the lever arm is actually the length from the point of rotation to the location at which the force is applied. The equation for that is the Greek letter tau. It's the Greek letter T, but it's called tau equals force times the lever arm. Torque is measured in Newton meters, and the force applied, of course, is measured in newtons, and the lever arm is measured in meters. So a couple of things affect torque, specifically three factors. The amount of force applied. If you apply a greater force, you're going to get a greater torque out of it. The direction also matters that you apply the force in. So you get the maximum torque when the force is applied at 90 degrees or perpendicular to the rotation that's occurring. And the location. So you get more torque when you move it as far away as possible from the center of rotation. It's much easier to open or close a door from the handle, which is at the end of which is on the opposite end of the door from the hinge, than if you try to push at the hinge of the door. So you might want to try that. You might want to go to one of the doors in your home and try to open it and close it by pushing on the doorknob, and now go close to the hinge and try to push the door and see how much force you have to apply. Less force is going to be applied farther from the center, so you can get more farther from the edge, so you can get more torque on it. That now leads us to rotational equilibrium. Now, when we talk about equilibrium, we talked about this when we were talking about forces in the last unit. It's the sum of all what's the sum of all forces acting on an object, or zero. Remember that translational equilibrium is when an object moves at a constant velocity because the net force is zero. The object could also be at rest, but it's following Newton's first law because all forces are zero. And you remember, equilibrium comes from the word equal, so the forces balance each other out. You also have something called rotational equilibrium. Now, rotational equilibrium is when an object with circular motion rotates with a constant velocity or at rest. So it's sort of like the torques balance each other out. So you have the sum of all the torques equals zero. So you have some examples like a balanced seesaw, or in lab when you're trying to measure masses and you're trying to get that triple beam balance, you're trying to get that that indicator to zero, you're actually balancing out the torques there, and you're attaining rotational equilibrium. So your rotational equilibrium equations, we have two of them. You have the force on at one end times the lever arm at one end equals the force applied to the second end times the lever arm at the second end. It doesn't mean that F1 and F2 are equal, or that D1 and D2 are equal. It just means that the product of F1 D1 is going to equal the product of F2 times D2. So again, and you'll have practice again on these in class as well. The other one is if you're talking about specifically weight, you're going to have the mass of one times acceleration due to gravity times the lever arm, and the mass of the object on the other end of the pivot point times the acceleration due to gravity times the lever arm as well. So these are the two equations we're going to be using. You'll generally be you'll have enough givens that you can easily find the unknown. If you have questions, please ask your teacher, and again, you'll get plenty of practice in class. We're going to finish up this discussion of rotational motion with universal gravitation. This is the law of gravity that we all follow. Isaac Newton is responsible for this as well. This came along with his laws of motion. And so he's given the credit for developing this, and myth has it that he watched an apple fall, or he was hit on the head with an apple. So he compared the moon to a falling apple and realized that if the moon wasn't falling toward the earth, it would have been shot off in a straight line away. So the moon, he conjectured, was actually in free fall around the earth. However, it just kept missing. So the law of gravity states that every object in the universe is attracted to every other object in the universe. So the reason that the moon kept falling towards the earth was due to that attraction. The moon and the earth are attracting each other. And everything in the universe pulls on everything else in the universe. So believe it or not, Jupiter has a gravitational pull on you, and you have a gravitational pull on the planet Jupiter. And it can be measured. But the Earth's pull on you is so much greater that it would cancel out any pull that Jupiter has. And you're also pulling on the Earth with the same amount of force that the Earth is pulling on you. So here's our equation for universal gravitation. We have our force of gravity, which is F sub g, equals the gravitational constant, which is that big G there, multiplied by the two masses that you're determining the force of attraction between, and you divide that by the distance between them squared. It's also known as the inverse square law. So if you notice, we have big G, which I said was a constant, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So it's called the gravitational constant. Again, M1 and M2 are the masses of the two objects, and D is the distance separating those objects, and you measure them from their centers.